5G network architecture. Mobile networks are mainly made up of radio access networks, transport networks, and core networks, which provide access, transmission, and control, respectively. 5G networks have the same elements. 5G core networks, often referred to as NGCs, consist of control plane function NEs, user plane function NEs, and other function NEs. The G node B connects to the control plane and user plane of a core network through NGC and NGU interfaces, respectively. 5G radio access networks are called NG-RANs. There is only one type of physical device, the base station. A 5G base station is called a G node B. G node Bs are interconnected through XN interfaces. 5G transport networks connect radio access networks to core networks and exchange data between radio access networks and core networks. 5G terminals access 5G networks through the new radio, or NR, to implement various services. In previous lessons, we learned that 5G networks will not only facilitate new consumer applications, but will also serve customers in a range of vertical industries. Network operators will no longer just provide the pipes, they will also provide new 5G services. 5G mobile internet and mobile Internet of Things will provide a unified platform for consumers, vertical industries, and network operators. 5G network architecture will have to flexibly adapt to the challenges presented by differentiated service scenarios and varied customer requirements. For different industry requirements, 5G networks need to support differentiated service quality requirements in multiple service scenarios. Therefore, 5G networks must be extremely flexible. Vertical industries require different security assurances, so different services on a 5G network must be isolated from each other. 5G network operators need their networks to be easy to deploy and maintain. They need O&M that has been automated based on the Internet architecture. As such, 5G networks need to be unified and open. Cloudification makes it possible to meet these requirements. This is the main reason for developing a cloud-based network architecture. Cloud-based 5G mobile communications networks have a reconstructed network architecture. They use NFV, or Network Functions Virtualization, on the core network, Cloud RAN on the radio access network, and SDN, or Software-Defined Networking, on the transport network. These new technologies allow 5G networks to flexibly adapt to different service scenarios and allow a single physical network to accommodate the needs of many different industries. Now let's take a look at the trend towards complete cloudification and some of the technologies used on 5G networks. Core Network Architecture. Architecture Characteristic 1 – NFV. Traditional core networks have a chimney-style structure, in which vendors use proprietary hardware, equipment is expensive, and resources cannot be shared. Software is locked into specific hardware, capacity expansion is complicated, and it takes a long time to deploy new services. 5G networks require flexible deployment because there are a wide range of service scenarios. The end-to-end arrangements or network resources that one vertical industry requires may not be appropriate for another, so the traditional chimney-style arrangement is not practical for 5G networks. Faced with the service requirements that a 5G network will have to meet, and in light of operators' needs for less expensive equipment, for improved resource utilization, and for agile rollout of new services, there is only one solution: cloudification of the core network. NFV decouples the software from the hardware. Device functions are deployed using a universal infrastructure. Software provides network functions, which improve O&M efficiency and makes the system more flexible. This is like how today's smartphones work. All the underlying hardware architectures of smartphones are universal ARM processors. Based on this universal hardware, users can install different apps to enjoy different functions. Architecture Characteristic 2 – Control and User Plane Separation, or CUPS. In traditional core networks, the control plane, or CP, and the user plane, or UP, are not completely separated. For example, in the 3G era, the PS domain of the core network consists of the Serving GPRS Support Node, or SGSN, and Gateway GPRS Support Node, or GGSN. The two devices process signaling and service data at the same time. The control plane and user plane are not separated. In the 4G era, the EPC consists of the Mobility Management Entity, or MME, Serving Gateway, or SGW, and Packed Data Network Gateway, or PGW. Compared with 3G, 4G core networks have a pure control plane device, MME. However, the SGW and the PGW do not work only for the user plane. For example, the PGW also needs to allocate an IP address to the smartphone, and this action is a control plane function. That is, 4G core networks do not completely separate the core plane from the user plane. Now, you may ask why 5G core network devices must support CUPS. In fact, if the user plane is separated from the control plane, it can be deployed on the access node closer to the users to shorten user plane delay. Traditional core network devices do not support CUPS and must be deployed in provincial capitals. As a result, base stations are far away from core network devices. In some provinces, the distances between the base stations and the core network devices are more than 500 kilometers, causing a large transmission delay. This does not meet the requirements of 5G low-delay service scenarios, such as ultra-reliable and low-latency communications, or URLLC. CUPS is a good choice for reducing the delay. User plane gateway devices can be installed in the data center, or DC, of each prefecture-level city. This way, the distances between base stations and core network gateways are greatly shortened, leading to far smaller end-to-end service delay. For example, for V2X services, we will deploy UPF, the 5G core network user plane gateway in Edge DC of each prefecture-level city. This shortens the distance between the vehicle and the server to 10 kilometers, reducing V2X service delay to milliseconds. This helps automated driving safer. Architecture Characteristic 3: Service-Based Architecture, or SBA. The 5G core network architecture also features SBA. This is modular functions. Every NE provides one function. Different services can choose different network functions as required. It is like eating in a restaurant. Traditional networks provide packages, but not everyone likes the side dishes in the packages. In the future, the 5G network provides the ordering service. Each person can select what he or she likes. Have you ever thought about the benefits of using this modular design for 5G core networks? Actually, the biggest advantage is the convenience of being able to create customized functions. For example, when designing an Internet of Things slice, most Internet of Things terminals are not mobile, so there's no need to provide functions related to mobility. In addition, most Internet of Things services have no special requirements on network bandwidth and delay. That is, quality of service guarantee is not required. Therefore, policy control and quality of service enforcement functions are not necessary and can be removed from the design. Therefore, with SBA, functions can be tailor-made to fit specific service requirements, which allows them to be deployed more quickly. Transport Network Architecture, or SDN. As IT technology has developed, the traditional model, where the software was integrated into the hardware, has been gradually evolving into a system where the hardware, the software, and the applications are separated into layers. The same thing has been happening with IP transport networks. With SDN, networks are divided into layers and virtualized. More importantly, the structure of transport networks has been getting simpler and simpler. The core concept behind SDN, the decoupling of control and forwarding, paired with flexible, programmable software applications, is borrowed from the design of PCs and mobile phones. But when this concept is applied to IP transport, it will create a shift in the industry, greater than when it was applied to PCs and phones. Cloud-based 5G core networks and 5G radio access networks are mainly driven by services, but cloud-based 5G transport networks are mainly driven by available technologies. The core technology of SDN is the decoupling of the control and data plans of the network devices, and deploying the control plane in a set of servers to become an SDN controller. SDN is like having a single brain in the middle of a network that can see the big picture. It controls traffic throughout the network, and this picture view enables it to optimize the entire network, transforming the way the network architecture works. The centralized control provided by SDN makes O&M simpler and easier. It allows for automatic scheduling and improves network utilization. SDN improves network openness through the use of APIs, greatly reducing the time required to deploy new services. SDN makes it possible to create differentiated network slices based on different quality of service, which are custom designed for the wide range of possible 5G service scenarios. Radio Access Network Architecture – Cloud RAN. 5G is developing fast, and with NFV releasing the potential of 5G networks, wireless networks are moving into an age of full cloudification. In a traditional network, a baseband unit, or BBU, is deployed at a wireless site. In the 5G era, wireless base stations are divided into two parts: centralized baseband units called CUs and distributed radio units called DUs. After the separation, DUs will still be deployed at wireless sites, and CUs will be centrally deployed in the data center. The CU processes non-real-time or NRT digital baseband signals that are insensitive to the delay, such as cell load control. The DU processes real-time or RT digital baseband signals that are sensitive to delay, such as radio resource allocation. The CU and DU communicate with each other through the standard F1 interface. This separate CU and DU signal processing is the foundation of the Huawei Cloud RAN solution. The CU has a Huawei server based on standard x86. It provides non-real-time baseband data processing for 5G base stations and uses virtualization technology to provide network slicing and a wide range of other services. The DU can adapt to many different coverage and installation scenarios. It provides real-time signal processing for devices like macro, micro, or indoor distributed base stations. The Cloud RAN solution allows for on-demand deployment and intelligent slicing, and can adapt to a diverse range of services. It can handle requirements for large bandwidth, short delay, and massive connectivity. Cloud RAN also implements resource pooling, resource utilization efficiency improvement, and flexible network capacity expansion. End-to-end network slicing. 5G networks are cloud native. Cloud computing technologies allow a wide range of custom quality of service-based network slices be rapidly created on demand on a single physical network. By keeping resources segregated, applications for a wide range of vertical industries can be supported without compromising security. 5G networks can bring countless industries together and promote integration of the digital and physical worlds. The 5G network of the future will be smarter, more agile, and more efficient. It will be an open network system based on SDN, NFV, and network slicing technologies. This lesson discussed the overall architecture of 5G networks. Physically, 5G networks consist of wireless base stations and data centers at all levels, which are interconnected through transport networks. In this physical architecture, the core network architecture and radio access network architecture can be flexibly deployed to provide end-to-end network slicing for various service requirements. That's all for this lesson. In the next lesson, we will discuss 5G network operation and maintenance.